Okay, we get to inverse kinematics. Even a couple of years back, inverse kinematics was such a dreaded subject. You know why? If you remember right in the beginning when we were talking about the 2R manipulator example, I was telling you about it is very hard to come up with a closed form expression. And in fact, in many situations, it's not even possible to come up with a closed form expression for inverse kinematics. And just to remind ourselves, what is inverse kinematics? Do you guys remember? Given an arbitrary end effector position slash velocity, you want to be able to find what the joints need to do to reach there, right? What are the joint angles for you to achieve a desired end effector position, right? So that's what is inverse kinematics. And I did mention earlier that the best way is to find a closed form solution, but it's not always possible. For very simple examples, maybe you could do it, but not for robots with large number of degrees of freedom. The other way is simply use forward kinematics, but solve for unknown joint angles iteratively. And as I was saying earlier, you need to be able to do this at every instant while a robot is moving. And so it can be a not very elegant way to do it. It is computationally intensive. It may not be able to solve it quickly enough for you to execute the next step in the motion. So the third approach, which is the most convenient as of today, and there are now a lot of subroutines already out there and packages are already out there that help you do inverse kinematics in this way, is the way using the velocity kinematics and the Jacobian. So just to remind ourselves, the end effector velocity, and for simplicity now I'm just writing V. So end effector velocity expressed in terms of the base frame is this JV times q dot. If you remember, JV is part of the Jacobian that relates to the linear velocity. Now, one way to think about inverse kinematics, which is, as I was saying, is a common approach now, is to not think about solving for the joint angles directly. You just think about solving for in which direction or in which way should I move the joint angles to get closer to where I want the end effector to go. So if currently end effector is here and I want it to go here, in which direction and in what proportion should I move the joints to get closer to my desired position, right? So you think in terms of a change or think in terms of a velocity, and that becomes a lot easier to execute. So you could also think of this if you're talking about small enough time steps, so you can also think about this as a delta V is JV times delta Q, right? This is not strictly true, but in the limiting case of time tending to 0 between consecutive time steps, this could be true. So if I go do a simpler calculation here, so delta Q, then if I take the inverse of this, I get JV inverse times delta V. But if you remember, JV is not necessarily a square matrix, so I cannot take its inverse directly. So I have to now use this other more fancy way of inverting a rectangular matrix. This is called the pseudo inverse, and you can read about it, and it has actually nice properties. So it's not strictly an inverse, but it is like an inverse, right? So and delta Q I can think of as Q at the next time instant minus Q at the current time instant is equal to JV pseudo inverse times delta V. And I can use this to find how to move my current angle by what amount to get closer to where I want to go finally, right? This is the basic idea. You don't quite implement it this way. You in terms of the implementation, you prefer to implement it in terms of the velocities directly. So you command joint velocities to be jv pseudo inverse times your desired velocity. But even here there are challenges. You don't directly implement it like this. You run into trouble for taking the pseudo inverse when you are close to singularity. So there is also this approach called damped least squares, where you add a small variable times the identity in your pseudo inverse process to avoid running into inversion problems when you get close to the singularity. So there is some amount of sophistication in what you can do here and how you can improve this computation. But the basic idea is you use the velocity kinematics, you use the pseudo inverse to figure out in how to move the joints, rather than trying to figure out what absolute angles or which angles, not absolute angles, they are still relative angles, but which values of angles you need to achieve, but rather you focus on what angular velocities you need to get closer to your desired position. And this in fact works quite well in an overwhelming majority of cases. And you will see standard methods that implement this with some level of sophistication, as I said, damped least squares, and you could add additional feedback terms and so on and so forth. So this is one simple way to do inverse kinematics without directly solving for precise answers.